In this tutorial, we're going to be learning about the behavior of the atomic size in the periodic table. The atomic size actually is going to be the distance between the nucleus and the valence shell, which is also called the outermost shell in an atom. Now, the distance is really dependent on how strongly the valence shell electrons are being pulled in by the nucleus, and that's called the Z effective. So we have briefly talked about the Z effective in a different tutorial. Now, when we go from left to right in a period, your Z effective increases. If the Z effective is increasing, what that really means, your electrons, your valence shell electrons are going to be pulled in toward the nucleus within a stronger force. And as a result, the size of the atom is going to decrease. So what I'm going to say here, when we're looking at the atomic size or the radius of these main group elements, so when we talk about main group elements, we're looking at the S block and the P block only. The Z effective increases as we go from left to right in the period, and as the Z effective increases, your atomic size is going to decrease. Okay. However, when you're looking at down the group, which is going to be top to bottom, we're going to be looking at it in a different concept here. So we really don't focus much on to the Z factor, but rather we focus on to the number of shells. So if I change the color in there, and I'll take an example of maybe lithium and sodium. So in a lithium, the atomic number is going to be 3, and electronic configuration is going to be 1s2, 2s1. And for the sodium, the atomic number is 11, which gives you the electronic configuration of 1s2, 2s2, 2p6, and 3s1. So what that really means, the last electron we have in the sodium is going to be in the third shell, whereas the last electron in the lithium is going to be in the second shell. And you can clearly see here they are in the different periods. So when you go down in the group, you're actually adding in a different shell onto those periods. So another way of saying that we have the lithium is in the second period, which means it's in the second shell. Sodium is in the third period, which means it's in the third shell, and so on. So when you increasing the number of shells, you obviously increasing the size of the atom. So if I'm focusing on lithium here, so if I go ahead and draw out the first shell, and then I'll draw out the second shell here. Oops. Okay, so I can clearly see I got 2 electrons in the first shell for lithium, and I got 1 electron on the second shell. But when I'm looking at sodium, I actually have now 3 shells to look for. That's my first shell, then I got the second shell right there, and then I got the third shell right there. So what's really happening here, the size is actually getting bigger. So I have 8 electrons in the second shell and 1 electron in the third shell. So as you go down the group, the shells are increasing. Okay, so when the shells are increasing, your atomic size also increases. So they behave opposite, but they do behave for a different reason. When you're going along the period, you focus on the Z effective, which increases, and that decreases the size. But when you look at the group, when you're going down the group, you are increasing the shells, and sometimes you may see in the books being said that the value of n is increasing. So n just means 1, 2, 3, 4 for the principal quantum number. Okay, so that also increases the size in there. So now let's focus on the trends in transition elements. So transition elements are going to be the D block elements. The D block elements size roughly stays the same. Okay, it has a small decrease, but occasionally you may see a small increase as well. But for the most part, when we're looking at the size along the period in transition elements, it's going to stay the same. So it roughly stays constant. All right, obviously when you're going down the group, it's going to increase because you're totally adding in a different shell onto the elements when you're going down the group. Okay, let's look at an example here to clarify things. So suppose I'm asked to increase these sets in order of increasing atomic size. So the first thing you want to look for if the elements are in the same group or in the same period. So I got the selenium, oxygen, and sulfur. So when I'm looking at in the periodic table to figure out where they are right here. So I got selenium right there, sulfur right there, and oxygen right there. And maybe I can change the color there to see it better. So those are the three elements I'm looking at. And since they are in the same group, we're going to be looking at, as you go down the group, your size increases. So what that really means, oxygen in this particular one is going to be the smallest in size, followed by sulfur, that's going to be bigger than the oxygen, and then selenium is going to be the biggest in this particular set. Okay, let's look at maybe another example there. Let's suppose I have magnesium, chlorine, and sodium. So my magnesium is right there, my chlorine is right there, and my sodium is right there. So I can clearly see they are actually in the same period now. So since then they are in the same period, I know as you go from left to right, your size decreases, and chlorine being on to the far right side here, it's going to be smallest in size. So chlorine is going to be smallest, followed by magnesium, and sodium is going to be the biggest in size in this particular case. Okay, let's look at another example here. Sometimes you may get a mixture where you have some elements in the same period and other elements are in different periods or in different groups. Like in this case, I have francium, calcium, bromine, and carbon, and they are clearly not in the same period or in the same group. My francium is right there, okay? Calcium is going to be right there. Bromine is right there. Well, bromine and calcium, at least they are in the same period, so that's going to be relatively easier to figure out. And then carbon is up there, okay? So anytime you are going in among different periods, your shell is mostly going to dominate. So for example, carbon is in the second period, which means it has only two shells, so that's going to be obviously smallest in size out of the rest of those guys. And then francium being all the way down, that's in groups in period 7 actually. So since it's in period 7, it's got 7 shells around the nucleus, so it's going to be biggest in size. So I can say carbon being the smallest, and then francium is going to be the biggest here. So now between the calcium and bromine, well, we can easily say that bromine is actually going to be smaller in size because they are in the same period. And since they are in the same period, when you go from left to right, your size decreases. So bromine is smaller than calcium. So this is what the order is going to look like. So anytime you have atoms or elements from different groups and different periods, so you may have to break them down a little bit to figure out who's going to be bigger or smaller in size. Okay, let's talk about the size of ions compared to the parent atoms. Now, when I'm looking at an anion, so suppose I have chlorine here and I make an anion out of chlorine to make a chloride, so Cl1 minus. So the number of protons in chlorine is 17, and the number of protons in chloride is also 17, because remember, that's just the atomic number. If you change the number of protons, you're actually changing the element. Now let's look at the electrons. So the number of electrons in chlorine is going to be 17 because it's a neutral. Now chloride having a 1 minus charge means it's going to have 18 electrons. So think of this. In chlorine, we have 17 protons working on 17 electrons overall that are outside the nucleus. However, in chloride, you have 17 protons inside the nucleus working on to attract those 18 electrons that are outside the nucleus. So it's like saying you have 17 people taking care of 17 people in case of chlorine, but then in case of chloride, you got 17 people inside the ring taking care of 18 people that's outside the ring. So it's going to be harder to take care of 18 people. So there is going to be a little bit of loose grip in case of chloride, and as a result, your attractive force is going to decrease because of the extra electron in there, and as a result this is going to be bigger in size than in case of chlorine. So it's always going to be true when you're comparing the anions to their parent atoms, anions are actually always going to be bigger than the parent atom. However, when you look at the cation, it's in a different story. In case of cation, you actually lose an electron. So suppose I take an example of sodium and sodium plus. So the number of protons in sodium is 11, and the number of protons in sodium plus is also going to be 11 because that's just the atomic number. And then the electrons in sodium is going to be 11, but the electrons in Na1 plus is going to be 10. So now think of this, you got more people inside the ring taking care of less people outside the ring. So there is going to be a greater control. It's going to have a better control toward the people that are outside, or toward those 10 electrons that are outside the nucleus. In addition to that, you can also think of this way. When you are sodium, the electronic configuration is going to be 1s2, 2s2, 2p6, and 3s1. But when you lose an electron to make Na1 plus, the electronic configuration is going to be 1s2, 2s2, 2p6. You lose the electron that's actually in the 3s, which is also the shell actually. So you completely lose a shell when you actually making a cation. That's not the case all the time. You don't really lose the shell all the time, but a lot of time you do lose a shell when you're making a cation. However, the scenario of having more protons controlling the less electrons outside the nucleus always going to be there, and since you're going to have a better control from those protons toward those less electrons outside the nucleus, in case of cation, it's actually going to be smaller in size than its parent atom. So as a result, I can say cations are always going to be smaller than their parent atom. So make sure you know these two big things about the anions being bigger than the parent atom and cations being smaller than their parent atom. Okay, let's look at isoelectronic series. So isoelectronic series means you have the group of anions that has the same number of electrons. Okay, and let me give you an example here. So suppose I have S2 minus, and I got Cl1 minus, then I got argon, and then I got K1 plus, then I got Ca2 plus. Okay, so let's focus on how many protons we have in every single case here. So number of protons in sulfur is going to be 16. That's just the atomic number. For chlorine is going to be 17. Argon is going to be 18. Potassium is going to be 19. And calcium is going to be 20. Now, when we're looking at electrons, well, we all going to have 18 electrons. So S2 minus means you got 2 extra electrons than the protons. 18 electrons in case of chloride, 18 electrons for the argon because it's just neutral, and we have 18 electrons for the potassium 1 plus and calcium 2 plus. So obviously these are called isoelectronic because they have the same number of electrons, even though they have different number of protons. So you can clearly see here when you have the same number of electrons, and as you're increasing the number of protons inside the nucleus, you will have a better control over those electrons. So another way of saying, calcium is probably going to have the best control over the 18 electrons because it's got 20 protons inside the nucleus, as opposed to your sulfide is going to have the least control over those 18 electrons because it has only 16 protons inside the nucleus. So we can clearly say as the atomic number increases, your Z effective is also going to increase because you can say the control kind of increases over the electrons that are outside. And since the Z effective is going to increase in there, your size is going to decrease. So that's one way of looking at it. And obviously you can also look at logically who's going to control the electrons outside the nucleus better, whether you will have 20 electrons controlling 18 electrons or 16 protons controlling 18 electrons. So we got 20 protons controlling 18 electrons in case of calcium 2 plus, and we got 16 protons controlling 18 electrons in case of sulfide. So when I'm writing down their order, I would say calcium 2 plus is going to be the smallest in size, followed by potassium plus, and then argon is going to be neutral, but then you will have chloride being bigger, and then sulfide is going to be the biggest out of all of those. Alright, so that's how you're going to be comparing the atomic size of elements, whether they are the ionic size or just the atomic size. If you have any questions, feel free to leave any comments in the section below.